Okay, so let's continue to the talk, and now probably we'll finish earlier and to make up that 15 minutes and, of yesterday. And we talked about that the reactions, the possible reactions, and the cross sections. And so this kind of active radicals produced in plasma, they can generate a new reaction pathway and to change the reaction process, either in combustion or fuel reforming or some kind of biomedical process. But also that the radicals or ions in generate, they could recombine very fast. And that you lost the chemical potential, but just recovering the heating. So in plasma, there are a few class of reactions. They contribute to the heating process. So one of the things that we talked about yesterday a little bit is that electron-ion recombination. So with electron and ions, that they take about probably a few hundred of probably a nanosecond, maybe to a microsecond, and then they can recombine together and generate heat. So if that ion does not collide with somebody else to generate new radicals, they become heat. Particularly at high pressure, recombination becomes a big issue. So the electron-ion recombination and the positive ion and the negative ion also recombine, they release heat. So this also that generates heating. So this process, they probably taking very quickly in a few hundred nanoseconds. It could happen. And there's another way that is the excited oxygen, and you generate electronic excited, and then you this electronic excited nitrogen collide with oxygen, you generate atomic oxygen, and then there's some energy surplus. This energy surplus, that is the collisional energy transfer, and they can generate heating too. And then the excited oxygen, they dissociate, and plus it's like hot atoms we talked before. They can generate heating. So this process is governing that the fast heating process of a plasma. That's the first peak of rising of the plasma process you saw yesterday in the figure. And there's some kind of slow gas heating. The slow gas heating normally is that because that I generate vibrational states. And everybody knows the vibrational state, if we want to transfer the energy to a transitional energy, it takes about hundreds to thousands of reactions, collisions. So that takes this guy, the energy relaxation from high vibrational states to the lower vibrational states, and it generated the heating. That takes a longer time. So this time we normally call a slow heating. It happens at 100 microsecond to probably a millisecond level. So this is 100 nanosecond. It's probably 100 microsecond to millisecond level, depending on the pressure. So this is a figure basically showing that the fraction of power and as a more fraction of oxygen and at a different pressure. So this basically showing you as you increase of the oxygen energy, the fraction of electronic power transferred to the heat is increasing. That means that we want to increase the fast heating of a process due to this process, and you want to put more oxygen into it to control the fast heating. If you don't want the fast heating and you want the slow heating about this process, you probably dilute the mixture with more nitrogen. So this can to control the timing of fast heating and slow heating. So this is a very important message you want to take it back. And sometimes you don't want fast heating to come. Someone you want to, and that you can change that by changing the concentration of oxygen because of this oxygen potentially participate in the fast gas heating process. And so in summarizing, and again that Andre provided that to me, and he's good to summarize all this kind of stuff. And that reaction pathway, and you have a argon, oxygen, nitrogen, hydrogen, all oxygenated fuels. And this ionization process generates a lot of all different kind of ions. The ions react with a reactants and they generate the charge transfer, become a negative or a more complex ions, where this is the new ions formed, and the electrons will attach it and become a negative ion too. You form all different classes of ions. These ions can recombine to generate fast gas heating. These ions can dissociate, they generate hot atoms because the energy is very high. And these radicals produced and this heat generated, they could accelerate a low temperature combustion reaction particularly. And of course, you can accelerate a high temperature reaction too because of the heating. So these are the two things of ion chemistry. And then you can draw the same diagram and for a major reaction pathways involving vibrational excitation. So I have an electron impact of this kind of reactants. I generate a vibrationally excited nitrogen, vibrationally excited hydrogen. If you want CO2 reforming, then vibrationally excited methane and CO2 could be important because methane and CO2 can be vibrationally excited in a broader electron energy range. And we are combustion guys, we don't worry about CO2 and those kind of things. We're talking about hydrogen and nitrogen. So these vibrational things, they generate a relaxation process from higher energy of vibration, go to the lower energy of vibration, and generate a slow gas heating, and at the same time produce some kind of radicals. So these are the energy transfer process. You got the electronically excited, you got the ions, you got this vibrationally excited, they generate fast heating, slow heating, they generate radicals, and these are the very complicated process. And some of these vibrational states can generate radicals and then change the reaction pathway. But what do I would say that in combustion process, this detailed reaction is poorly understood. So, but theoretically, I summarized yesterday that the major reaction pathways I summarized here. These are probably the major reactions. If you study plasma or specific combustion, even though there are many, many ions or whatever reactions, hot electrons there, but don't look at them in the beginning on those reactions. Look at the reaction that can potentially compete with the chain branching reactions and chain initiation reactions or combustion. So those set of reactions are the ones you probably have to take a look. For example, electron impact dissociation, electron impact excitation of oxygen and vibrational oxygen, and then nitrogen electronic excitation generate dissociation, O1D reaction with fuels, and then nitrogen vibration at a high electrical field strength. So these are the process. You probably want to look at it and then to see how they impact on the combustion process before you look at the details. So as I said yesterday that the plasma can generate all these kind of things, but some of them, they have a very long lifetime. For example, NOx and ozone and a few fragmentation, they can last very long. And some of them, they are O2 singlet, they also last very long, but radicals can be very short. And the vibrational energy can be longer too. So this is a time scale is very important when you compare your combustion time scale. Not only the reaction rate, but also the time scales, for example. So the question that how does these things really affect? And then there are some of these guys a very short time scale. So we need a very kinetic experiment to tell that how this reaction species really affect the reaction rate.
Do you have ballpark numbers for those time scales? Like very rough.
Which time scale, for example? Which species? NO? Radicals that in a combustion person certainly know what is the time scale of radicals can survive, right? And probably most of the radicals, I think the time scale depends on temperature. Higher the temperature, lifetime is longer. But normally, let's say in plasma, normally you're talking about the temperature below 1,000 Kelvin. The old radicals recombination, I would say that probably the lifetime probably about a millisecond or shorter, then will be dying. So you look at each fraction reaction will quench your radicals, right? So, and then this one probably even shorter. This time scale, N2 ABC, I would say that the time scale is about less than 1 microsecond. So there will be disappear, okay? So the first thing is that how much that the plasma reaction really change that the combustion process? As I said before, you have to compare the reaction rate, not how fast. I mean, how fast is the time scale. You generated this, electrons generated these radicals probably in 10 nanoseconds. You probably produce these radicals. But how much you produce, that's the problem, right? If you produce too little, you do not change combustion very much. But you produce a lot, that is, you change the combustion process a lot. What do you mean by few a lot? You compare with whom? You compare with the major chain branching reactions. Okay, that is at the target you compare. For example, at high temperature combustion, that H plus O2 reactions and O plus H2 reactions, these are the dominant chain branching reactions. So if my plasma can produce something faster than that, that means I can control the combustion process. If the plasma can, the radical production rate is slower than that, that means my role is limited, right? So I plot this reaction. If you look at the reaction flux, that means that is the reaction rate, right, generated by plasma. And with an electrical field at 500 tonsend, 200 tonsend. Now you start to have a concept. What does it mean by 500 tonsend and 200 tonsend, right? It's a very strong plasma, right? Anything above 100 tonsend is a strong plasma. So even at 500 tonsend, probably it already break down of the air mixture. And then this is the reaction rate of plasma. Let's take the vertical one, 1500 Kelvin, where the flame will die. At 1500 Kelvin, the flame will die. If you look at that the H plus O2 reaction, this is the major chain branching reaction. If you're looking at here at 1500 Kelvin, they're almost greater or equal to the plasma generated radicals at 500 tonsend, right? So what it says is that it said that at the flame extinction conditions at 1500 Kelvin, the radicals production rate by plasma is equal or less than the chain branching reaction by combustion itself. At high temperature, you don't need to consider because that the chain branching reaction by combustion itself is faster than you do, right? That again, this is another evidence that the plasma cannot control much about the kinetic effect at high temperature. Rather, to produce fast heating and slow heating to produce the heat and maintain the combustion process. But if you're looking at the temperature below 1500 Kelvin, so you have a chain branching reaction is getting much slower, let's say 750 Kelvin, you got a great chance of plasma to enhance ignition. Because at 700 Kelvin, you don't have flame, right? You have ignition. If you really want to control ignition, if you really want to control low temperature reforming, plasma is a great thing to do. And if you're looking at that the proxy radicals, proxy and H2O2 dissociation, this reaction is very important around 100 Kelvin or below for radical production. So at 1000 Kelvin or below, you can see the plasma is several order of magnitude faster than that reaction. So plasma give you again at 500 tonsend, a strong plasma. So the plasma process provide an effective way to bypass the traditional chain branching reaction at the low temperature so that it can control the ignition process, right? Fast ignite. That's why that in a shock tube experiment, if you fire plasma, the ignition delay time is shortened by 2 orders of magnitude. It's because of the gap here, right? At high temperature, you don't do much things. You only control the chain initiation reactions. You shorten the ignition delay time normally by chain initiation, not by chain branching reactions, okay? So this is the something, and just to keep you in mind. We look at the chain initiation reaction of hydrogen and oxygen is really slow. And plasma has the opportunity even at 2000 Kelvin. If the ignition is a problem for hydrogen, you want to accelerate, even at 2000 Kelvin, plasma is great because the first radical produced by this reaction is down slow, right? So that gives you something, what you can control, what you cannot. And let's look at the reactions, a few reactions. This is at the a reaction rate I plotted, published by who is Sturrock. Sturrock is a professor, and Sturrock is a theoretician, just like Stephen Klippstein, in the field of plasma combustion. He computed a lot of reaction rates, and but does not claim that uncertainty is 30%. And so if you're looking at this reaction, right, H plus O2 reaction on the ground state, this is combustion reactions. That reaction is here. Okay? What if the oxygen is electronically excited to singular delta? So here that is the H plus singular delta reaction, and then generate a branching reaction is somewhere here. So you can see that at 1000 Kelvin, you can see the H plus O2 reaction compared to a H plus A2 singular delta is faster. At high temperature, it doesn't matter anymore. At 1000 Kelvin, it is here. So what it says that if you can generate a O2 singular delta with 1 electron volt, potentially it can change that the chain branching reaction ratio for below 1000 Kelvin, right? So this is that again the reaction rate. And the second thing is that is the methane plus oxygen reaction. This is ground state. This is that reaction in GRI or chemically, the kinetics. But what if that oxygen is a singular oxygen, and you generate this reaction rate? So this reaction rate again is about 1 order of magnitude higher than the chain initiation reaction by the ground state of oxygen. So these two elementary reaction rates give you the possibility that you can control the branching reaction rate, you can control the chain initiation reaction rate by creating excited oxygen, 1 oxygen singular delta, right, with 1 electron volt. 1 electron volt is not energy, and if you look at the CO plus oxygen reactions become CO2, and then you can see that if you oxygen, you can generate this reaction rate is much higher, and with B sigma. So you wanted B sigma, and to generate a CO oxidation. This is important for reforming, low temperature reforming. If you were reforming something, and that is probably important too. And then you think about the reaction I just talked about before, electron impact generate O and O and D reaction, and the electron impact of these reactions. This is that the reaction rate constant. In many cases, if you have a strong electric field, 200 to 800,000, instead of E plus oxygen generated 2 ground state, the probability is much higher to produce O and O1D. So if your electric field is very strong, you don't need to consider this reaction. Instead, you have to consider this reaction, because that. So then the reaction rate is O1D reaction with the fuel. How fast is that? Anybody knows? I think a few people knows, really, particularly for large alkanes, jet fuel, whatever. There's no experimental data at all, no theoretical study at all. Anything you do in the laboratory would be new, would be publishable. If you want to publish a paper, working on this problem is easy to publish a paper and to find a job, maybe. And rather than try to measure something really not important, something. So that's what I always talk to Stephen Klippstein. I said, you better to using your tool to branch into other field, to do something far more impact, not to looking at 5% of uncertainty of the reaction rate. You care? Yes. I care? Yes. But industry care? Don't, right? Industry said, okay, give me a software predicting me 30% uncertainty, I will be very happy, right? So always that research try to do is that, guys, I want you excited. Do not do anything below 10%, okay? That kind of thing is not important. I'm not saying not important. Does not excite you, okay? Doing something does not exist. Doing something nobody knows what you're doing. Doing something that maybe have big impact. Okay, that's what I'm trying to say. This is something that somebody can measure O1D reaction with a large jet fuel inhabitants, even for methane. I'll be very interested in and to know the data. Okay, the field. Question?
I had a question on the previous slide.
Previous slide? Okay, go ahead.
Does the figure on the right take into account would probably be an increasing population of electrons as you increase temperature, or is it a fixed?
This is the fixed. This is the reaction rate. Is that basically that the single, for example, if you have a single molecular, single electrons compared to a single. If the electron number density is overwhelmed, that let's say that H radicals, that would be great, a higher rate. But normally electron number density, the weak, let's say non-equilibrium plasma, electron number density normally is very low.
Even at higher neutral gas temperatures?
Even at this temperature, electron, yeah, probably is low. Yeah. If you get into that the 5,000 Kelvin, that's a different story. Normally at 2,000 Kelvin, it is the vibrational and oxygen excitation, right? Go to 3,000 Kelvin, slightly some kind of dissociation. And then for ionization, you have to get at a much higher temperature to generate a high electron.
For a typical gas.
Yeah, yes, correct. Well, what I was talking, I get lost. Okay, doing something important. Okay, doing something, not doing some kind of decimal type of research, always. So this is I showed you yesterday. I don't want to show again. Is that this will be the diagram? I really love it because that I give you some kind of order of magnitude where that the plasma can potentially impact combustion. It is where is the heating effect and where is that chemistry effect, and then so in the plasma that I try to show you some kind of not decimal type of work is that they're using a plasma to control cool flames. And if you're looking at this ignition delay time as a function of temperature for N-heptane as a lean mixture, at 1 atmosphere pressure, at the ignition delay time is about 1 second, right? 1 second. You need 1 second to generate a low temperature ignition. But for around this temperature is about 1,000 Kelvin, probably around here. It's about 1,000 Kelvin. This is about 1 second. So therefore, and you never can see a cool flame in laboratory. Because in countable flame, the resin time probably is 10 to 100 milliseconds, right? In a Benson flame, the resin time probably less than 100 milliseconds. You never can see your cool flames, right? But if you believe plasma can enhance low temperature chemistry, you should be able to do experiment even with 10 millisecond resin time. You should be see a cool flame in the lab. That is a proven of plasma really can do a big deal for low temperature flames, right? So after I draw the figure to write my review article, and I thought about this, and I said, okay, I told my research staff at Shanghai Wang, I said, let's do experiment. Using plasma to control the combustion, we should be able to plasma assist the cool flame. Even in a countable flame, you should be able to see it. But he didn't believe me, and he waited for probably 1 year, did not do the experiment. Until one day I really cannot wait. I just said, you do experiment this afternoon, otherwise I didn't say. And I said, okay, so 3 o'clock, and he called me to my office. Professor Zhu, I saw the cool flame there. I could fix that, Jesus, that's great. So we published the paper in Symposium. We won this distinguished paper award. So it's very simple. And actually, looking back, it's really a very simple experiment now. Then we learned how to do a cool flame with plasma. But during that process, we knew that without plasma, you can also create. But it's difficult to, without plasma, to do it. And in the beginning, once you learn that skill, you learn. Right now that we have several people in my lab, Chris is doing it there, and he can create a cool flame without plasma, right? So the only thing that for large hydrocarbons, and you have plasma general radicals, and then you go to small alkanes, you go to the RO2, depending on the temperature. High temperature goes this way, low temperature goes that way. So if you have a plasma, and then this is the ignition diagram. This is temperature, and this is at the residence time. If a fuel has low temperature chemistry, so you have a ignition, low temperature ignition, and you have a extinction, and between this you have a transition from low. This is the cool flame. This is that how cool flame transfer to a high temperature flame. This is that the basically S curve expanded into a to consider cool flame. What if you have a plasma? And you know that the plasma enhances ignition, and plasma enhances low temperature ignition more than high temperature ignition. So, therefore, schematically you can see this low temperature ignition will be dramatically shortened here, and this a cool flame probably will be affected less. You generate this kind of a curve. This is high temperature flame. This will be cool flame. This will be, if you further increase the plasma, you generate everywhere ignition with high temperature. So theoretically, you can generate a cool flame in this region with a much shorter residence time compared without plasma. It's a very narrow window without plasma. You can see it, but here in a broader window should be see a cool flame. That's basically the. I draw this diagram before we do the experiment, and then this is that the experiment you see in the laboratory. You can using a fuel which is at I think that is N-heptane. And you have oxygen and with a plasma discharge to generate some kind of ozone, for example. And then at the same condition, if you ignite it with a high temperature spark, and you create this kind of diffusion flame and generate a lot of soot from the fuel side. If you don't ignite it with a spark, you ignite it with a laser or you ignite it with a low temperature igniter, and you generate this cool flame here, the maximum temperature probably 700 to 600 Kelvin. So with the same boundary condition, with the same strain rate. So this proves that with a plasma sensitization, you can shorten that the cool flame chemistry time, allow you to be able to absorb cool flame, which you could not do it without plasma. So this also concludes that indeed that plasma play a great deal to enhance low temperature chemistry so that you can see a cool flame in a very short residence time. And this is a numerical simulation. You can see that this is at the flame temperature as a function of strain rate. This is a high temperature flame, 2400 Kelvin, and then extinguish here. And this is at the cool flame branch. If you do an experiment in this range, you should be able to see the cool flame. And if you reduce that the fuel concentration from one side, you can see that this extinction limit of high temperature flames move toward here, and this guy, it does not change much. That means that at lean fuel conditions, you have a broader range to see cool flame. You have a narrow range to see a high temperature flame. So that is a very interesting thing about the plasma system combustion. So in the laboratory right now, Chris Ryder, and he's around here, can talk to him. He was able to see a diffusion cool flame. You just see it before. He would be able to see a premixed cool flame, and also be able to see a dual diffusion flame with a partially premixed, the diffusion cool flame on one end, and the premixed cool flame on the other end. You can see that they publish a lot of papers. It's very easy. Anything you write, you can publish, because no one has done it before, right? So doing research, you really want to be the pioneer. You don't want to be followed. You don't want to be better. You want to be pioneer. Okay, that is something, and you really want to do your career. To chase somebody in the same field is really difficult. But if you create a different dimension, it's easier, much easier, because no one in front of you, right? So, and eventually somebody chases you if he has more research money, but then you create another dimension, and then you go somewhere else. So I share you with one story. So anybody from Harvard from here? No? So when I was coming to Princeton in 2001 as assistant professor, there's one genius guy called Zhigan Suo at Harvard, the mechanics. He already was a professor at Princeton, and he asked me, Yiguan, what are you going to do? I said, I want to do combustion theory. He said, wait. Combustion, just a candle flame? Nothing more to do. I said, what to do? He said, doing micro. I said, why do I have to do the micro? You see, the mechanics, we do a mechanics, the bridge, the building, and the fracture. That mechanics has been studied for decades. Not much to do. What I'm doing, micromechanics. Used to do microcombustion. I said, well, it's interesting. I jumped to the microcombustion area. At that time, Paroni and Professor Fernandez Payo, they already started. But most of them, they are doing experiment. But I developed theories for them. The theory showing so many things they could not explain with the experiment. So that really, I got excited for that. But there's no money to support. Nobody supports that money. Army does not support me. The NSF does not support much. So then I jumped into this area of plasma combustion. I thought that plasma people don't understand combustion. Combustion people don't want to jump to understand plasma. This is something I can do in my territory. And that I wrote a proposal to NSF, to Air Force Program Manager at that time, Julian Tishkov. And he said, oh, this is something interesting. But as long as you can collaborate with the Air Force, we're going to fund you. And I said, I don't know anybody in Air Force because I am not graduated from this country. And he said, I give you a phone number, you call him, he will respond to you. I called him with Cam Carter. Anybody know Cam Carter? Yeah, you know, the diagnostic guy. And then we started for that. We funded by him for 11 years in this area. He pretty much built my career. So at that time, nobody was working on this. Right now, that is, you create an area that people invite you to different conference, right? I just received the invitation to go to Golden Conference of plasma processing. I don't have time to go, but I think that you create something which does not exist. You pretty much build your name in that area, and then you grow from there. That's simple. Then in 2010, I was in Germany. That the Humboldt Foundation gave me a research award, and then they had a ceremony. The president to shake hands with everybody, had a dinner with everybody. There I saw a guy, almost lost his hair. It's Zhigan Suo, and he moved to Harvard. Zhigan Suo asked, hey, Yiguan, what are you doing? I say, I'm doing combustion, austere combustion. So I'm reading a book of Froman Williams' book, Combustion Theory. I said, why do you want to study combustion? He said, know what? I did micromechanics. And then after a few years, micromechanics already too many people, and I wanted to do a nanomechanics, and go nanoscale mechanics. And I did a few years. Nanoscale mechanics is pretty much populated, and I tried to do soft materials. And soft materials, what? If you stretch it, the bond may be broken. The bond broken is a reaction process. I need to learn what is a reaction, what is combustion, because it generates heat. So he created a new area called soft mechanics. So he is always in the frontier in mechanics, and do a few years and then move to another area. Now everybody just follow him, just like hair. So this is the true pioneer, and then you really have to do this. If we want really to measure more accurate, that is important too, unless you're really excited and enjoy by it. Moving to a new direction, moving to a new area is far more entertaining and enjoyable. This is gossip, okay? Are you ready to move forward? Oh, that's it? Chemistry? What is that, chemistry? So, okay, that's it. So I probably stop here today and give you 15 minutes. Tomorrow we talk about a diagnostics of plasma-assisted combustion and the modeling of plasma combustion, and discuss a little bit perspective, what is need to be done, what will be the future areas. Okay, you any comments and any questions? So okay. So if you want to discuss about anything, I will be happy to share with you. Okay, thank you.